Hi everyone, it's Prof. K speaking, and this video is going to talk about classifying chemical reactions as precipitation reactions, and it's also going to dive a little bit into solubility and how we predict it. Our learning objectives for today are to define three common types of chemical reactions, but specifically, we're going to talk about precipitation, and my next two videos are going to talk about acid-base reactions and reduction reactions. And in order to help us predict and describe precipitation reactions, we're also going to practice predicting the solubility of common inorganic compounds using some solubility rules. And so what is a precipitation reaction? I talked a lot about one in my last video, but I want to officially define it here, and then we can dive into what it looks like and how we predict solubilities. So precipitation reactions are reactions where dissolved substances react to form one or more solid products. So in the last video, I covered the molecular equation of lead nitrate interacting with calcium chloride to form dissolved calcium nitrate and the precipitate or the solid that forms lead chloride. And so in this reaction, we have several dissolved compounds interacting to form a solid product. So this is a precipitation reaction. And in nature, there's a lot of really interesting precipitation reactions that are actually really important for the functioning of biology, for the formation of ecosystems. And so coral reefs are the result of the precipitation reaction producing calcium carbonate. Kidney stones are also a precipitation reaction. Undersea vents lead to the production of metal sulfides. Stalactite formation is also calcium carbonate. Eggs are also calcium carbonate. So calcium carbonate is sort of a precipitation reaction that's all around us. Industrially, there's a lot of cool precipitation reactions that are needed to produce the things we like to use every day. So commodity and specialty chemicals, some medicines are precipitation reactions. Oftentimes, separation processes utilize something precipitating. If you want to capture CO2 and store it, one way to do that is to mineralize or to combine that CO2 with some mineral to capture the CO2 from the atmosphere. So precipitation reactions are super important for how the natural world works and for how we're able to do interesting chemistry. But in order to sort of do cool precipitation reactions, it helps to understand why they occur or where they come from. And solubility explains why we see precipitation reactions. And so solubility is a quantitative or numerical expression of the extent to which a substance may be dissolved in water usually, but it can also be described for any solvent. So you could talk about the solubility of something in oil. A lot of times in this course, we're going to talk about solubility in water, but that doesn't necessarily have to be the case. And so if something is very soluble, what that means is that we can dissolve a lot of it into water or whichever solvent we're using. And so salt is something that we often describe as being very soluble because you can add a lot of salt to water before you start seeing that salt as a solid. So you can put a lot of salt in something and it will just dissolve and look like water. If something is insoluble, what that means is that there are very low concentrations of that substance can be dissolved into water or the solvent. And so it doesn't take long of adding whatever the solid is to that solvent for it to just look like that we have solid product here. So it's not really falling apart in the solution. And so if we want to draw sort of a representation of this, if we have some range of very soluble to soluble, and we'll just pretend I'm putting in something labeled AB2, some unknown compound, AB2. If AB2 is very soluble, what you'll see is A2 plus, B1 minus, B1 minus, A2 plus, B1 minus, B1 minus. And so the second we add it to the water, it just sort of falls apart and it drifts about as ions. If something is somewhat soluble, you might have AB2 on the bottom and A and B sort of floating around in solution. And so we have some combination of solubility. Oh, I switched. Okay, B1 minus. So there is some solid that we see on the bottom of our beaker, but a lot of it is dissolved. If we're talking about something insoluble, if you add it to the beaker, normally we have a lot of AB2 on the bottom, and then maybe we have just a little tiny bit dissolved. So it's not to say that none dissolves, but that very little dissolves. So most of it is sort of hanging out at the bottom as solid. And so this is a reaction that's insoluble. AB2 in this situation doesn't like whatever it's hanging out in. And so one of the questions that a lot of students tend to have, and even people who've been in the field for quite a while, is how do we talk about something being soluble or insoluble? How do we predict solubility? And so there are tools developed which you'll be able to use in this course, which helps you predict solubility. And so this is a table in your book, table 7.1, that you'll also be using on the test to predict solubility for these compounds. And so I have a few sample compounds here that we're just going to work through this table so that you can understand how to use this table. So my first example is ammonium chloride. I want to know, is this soluble? So I go to the table and there's a set of compounds that are typically soluble. And included in that is ammonium. And so what that means is that ammonium is typically soluble with the exceptions of none, which means that this is definitely soluble. Oh, sorry. This is soluble. And so if we have something in this group, it's likely to be soluble. So I mentioned before, NaCl, salt, is also soluble. And so now if I'm looking instead at something like silver chloride here, if I'm looking at silver chloride, I would first see if it's in my soluble ionic compounds. So I don't see silver anywhere in this first row, but I do see chloride. And so it says that chloride is typically soluble, except if it's combined with silver, mercury, or lead. And because this includes silver, this is not soluble or insoluble. And so that's how I'm sort of reading through this paper, or through this table. And so our next compound is mercury chromate. And so I don't see mercury. I don't see chromate over here. If I move to the insoluble ionic compound portion of the table, I do see chromate. And so what that tells me is that this is also insoluble. And the only exceptions to this rule are if we go back to the solubility table and we're in this group 1 cations or ammonium, then maybe it would be soluble. But mercury isn't included, so this is insoluble. And this last one is a bit of a practice for what the magnesium chlorate is. And so if something has magnesium here, magnesium, and then chlorate, which is ClO3 minus, yes, magnesium chloride. So if we look at this table, I don't see magnesium anywhere, but I do see chlorate, and it's in my soluble ionic compounds. So this is also soluble. And so this is how we use this table in order to guess the solubility of various compounds. So now I want to return to my example reaction from the last video, which is to say I wrote the molecular equation of lead nitrate plus calcium chloride forms calcium nitrate and lead chloride. And I want to know if I was correct in saying that lead nitrate will dissolve, calcium chloride will dissolve, calcium nitrate will dissolve, but lead chloride won't. So I'll return to my table and I'll look at these compounds and I'll say, okay, lead nitrate. So let's try to find lead. I don't see lead anywhere, so let's try to find nitrate. Nitrate is here. And it says that there are no exceptions to it being soluble for nitrate, which means that for both the compounds that contain nitrate, I know these have to be soluble, which means that they can be written as sort of aqueous or dissolved. Calcium chloride, if I look at this list, I don't see calcium, but I do see chloride, and its only exceptions are silver, mercury, and lead, which means that calcium chloride is also soluble. However, since lead is one of the exceptions, it's insoluble, which is why when we looked at our precipitation reaction here, we can confirm that lead chloride is the solid precipitate that forms when you dissolve these compounds, and that the calcium nitrate would stay dissolved in the solution. So we know what the precipitate is using these solubilities. So this table helps us predict what happens in precipitation reactions and helps us confirm if something is a precipitation reaction. Because if I had done the solubility prediction of all these compounds and they were all soluble, then that means that reaction is not a precipitation reaction. Nothing will form or fall out of the solution here. And so this is a tool that we will use to start to look at precipitation reactions and to start to predict solubility using this table.